We had lots of ideas.
Okay. Would you like to share the one you have the most confidence in?
Our model of human growth, or population growth.
Okay.
Just y is equal to a to the x, whatever a needs to be, if I write to model that correctly. It was just on the homework, it just reminded me of that.
Oh, okay.
I didn't write a discrete dynamical system, but you just said write something that models something with a minimum.
That would have a minimum population. How do you know that that has a minimum population?
Because there's a horizontal asymptote, and because hopefully humans don't go extinct.
Okay. Let me clarify. Well, I'll clarify a little bit about what I mean by minimum population. The idea is, if this is our population up here, this is time down here, it is in one sense, and we'll see it acting this way, like a horizontal asymptote. But it's not a horizontal asymptote in the same way that the maximum population is. So the idea is, well, if I start my population up here, what's going to happen is it's going to go up and head towards that maximum population, just like what we saw with the flu. But if I start down in this region here, not at 0, I actually have some wolves. But below this minimum threshold, what happens is the wolf population will dive and go extinct. And so this guy right here does not act as a horizontal asymptote for the graph of the population. It's a horizontal asymptote in a little different way. Crystal?
Well, our group kind of just added in minus m to our little thingy. We had the same equation, but we had k, and instead of just wt, we had wt minus the minimum multiplied by, yeah, you know what I'm talking about.
So if we use little m for the minimum population, and then you left capital M for the maximum population.
That way, if the number is either less than the minimum or greater than the maximum, then growth will be negative.
So we just shifted the 0 from 0 to the minimum.
So if we take a look at this, simplify it a little bit, so we'll just call this y. And over here we would have k, x minus little m, big M minus x. This has zeros at big M and little m. So little m and big M. Between these two, this is positive or negative?
Positive.
Positive. Up here it's negative, down here it's negative. So we know these are our equilibria. That's where our change is equal to 0 because y represents the change in the population. And so, sure enough, we start above the minimum population, we're going to change in a positive way, so we're going to go up, level out at our maximum population. If we're above the maximum population, we dive down. If we're below the minimum population, we dive down as well. Anyone see any issues at all with that model?
We're supposed to. Just a chance if you're getting that negative change, how do you know you're not above the maximum?
Well, as soon as if it gets down below the maximum again, then it will rise up again.
And all I was asking for was that if you're below the minimum, then you would go extinct. Your population numbers would decrease.
So does that actually happen though? Like if there were only like 4 wolves left, would those like undeniably like die?
It would depend on the actual structure of the wolves that you have.
Okay.
So it is more complicated than just once I get down to 4 wolves, it's all over.
No, I mean, just like more generally, like if you have a certain creature,
yes.
Is there like a minimum and
There
then
are-
they die?
There are
Like, if it
minimum
gets to
populations for them.
Yeah,
Yes.
well, yeah, if it gets to 1,
Or
it's not pregnant males.
No, it's worse than that. It depends on the creature and how what its behavior is like. If you take something like wolves, which are territorial, and there it's a little more dependent on the female population than the male population, because a single male will have, they're polygamists. And so, but if you drop below a certain population, and of course in the real world it's not as hard and fast as we're drawing it. But if you get down there, what happens is over the course of a winter, you'll get enough deaths that you won't have healthy male-female combinations to create new litters and things for the next year, and so you'll get then a steady decline out of that. And then, especially when you deal with populations where it takes several years to reach maturity to where you're reproducing, again, if you drop below certain numbers, it takes so long for it to try and get, you know, a reproductive population back going again that what happens is you die in the meantime. So yeah, there are minimum sustainable populations as well as maximum sustainable populations. There is one issue with this one. Who wants to tell me what it is?
Maybe this is going beyond what we're talking about, but we're not really modeling like I'm just thinking predator-prey models.
So it is definitely a simplified model, and we're not putting in all of the real dynamics that happen in the world. That's going to be true of all of our models, but there's actually a structural flaw with this.
This is what I was thinking. We're just making sure, essentially, to make sure that big M is bigger than little m. But
well, yes, that's excellent.
it's not
Thank you.
structural.
That would be an issue. No, there's actually a little structural flaw with this one.
Great. Is it that the minimum population is 0?
You're getting there. The minimum population, really, if we want this to be physically reasonable, we would need to put in that condition as well.
I mean, I guess there should be another 0 at 0, right?
Why?
Because once you have 0 wolves, you're not going to have any sort of change in wolf population.
So 0 must be a,
0.
give it another word.
An intercept, I guess.
Move back up to this one. It needs to be an equilibrium point. So 0 is an equilibrium, and so it would be nice if our model had that fact in it as well. That 0 is an equilibrium point for the population.
WT on the end.
And so we just we put in our WT. That goes back to the idea, if we were to say this in words, what we're saying is that the number of new wolves I get depends on how many wolves I've got. The more wolves I've got, the more wolves I'm going to get. It depends on how far I am away from this minimum population, where if I drop below that, everything goes south. I wonder why we don't use south as a pejorative. Everything goes east, north, northeast. Everything dies. And it depends on how close I am to the maximum population, because once I get close to that, then I'm eating all of the food and everything, and so I have people starving, and so the number of wolves that I get decreases because of starvation and those kinds of issues. So that one takes into account all three of the things. And so we would see this kind of behavior. What happens if you're below 0 in this model?
Population increases again.
Yeah, if you do it, if I plug negative values in for x here, that's going to be negative, that's going to be positive, that's going to be negative, so I'm going to have a negative times a positive, so that's going to be positive. And so if I started somehow below 0, I would come back towards 0. Not that that's physically reasonable, but the mathematics works.
That's how the equation is.
So if we come along, maximum population is what kind of equilibrium?
Stable.
Stable again. Minimum population is
Unstable.
And this time the 0 population is
Stable.
so we get those. Questions about the model or how it operates? If we really wanted to apply this to the wolves, what would be the process that we would go through? If we actually wanted to find this model for the real wolf population in Idaho, which if we wanted to, we could go online and we can get the data, tell you how many wolves there are every year since 1995. How would you use that real information to actually put real numbers in this so that we could start making predictions about what was going to happen to the wolf population in the near future? How many hunting licenses to give out, since they now allow hunting of wolves. In fact, I've got a couple of neighbors that have wolf tags, and so forth and so on.
That'd be scary.
Oh, they thought I have this one friend that's hunting is his life. He didn't have to work for a living. So he abandons his family for a month or
Goes down to the wilderness.
goes out into the wilderness with his buddies, sits in blinds, shoots things. If he weren't such a nice guy, I'd probably take it up with him. So what would we do to actually try and figure out a model we could actually use to make predictions, actually get some numbers into this thing?
Random regression, because what, we don't know K, little m, or big M, but with data we have some Y's and X's. What would happen?
Right, so with some data, we would know WT, and we would know WT plus 1, so we would know the change, we would know the WT values, and so we could put that in, put several of those in. That would give us a system of equations, and K, little m, and big M. Unfortunately, it would be a nonlinear system, but we could try and go and solve that, figure it out. Good.
Well, I mean, if you have 4 points, then linear algebra says you can find a solution to your system of equations.
Problem is, this is not linear algebra.
But can't you use linear algebra to find?
This is, here you're going to have things like K times negative M times big M, just a negative M times a big M, a K times a big M, a K times a negative M. If you were to multiply that all out, you would have several nonlinear terms.
Okay.
And no, nonlinear dynamics are very different from linear. Nonlinear algebra is a great deal more fun. Wild things happen. But we could go and try and solve it that way. See if we couldn't work it out.
Don't we, I mean, we already know the value of little m, though. I mean, because they had to decide how many wolves to put in, so they had to know how many they needed for
So
sustainable.
we could go to the biologist, we could look it up and say, okay, well, how many did they line up first? We'll figure that's about the minimum population, so we can plug that in. Any way to get an idea for maximum population?
See if it ever hit a point where it got to numbers and dropped, or
Yeah. So if we get to a point where it started to drop and just kind of bounce a little bit or something like that, that could help us have a guess for a maximum population. Once we have that, then we can do regression to find the K the same way that we did last time with the flu. All right. So there's a lot of different approaches that you could take, some purely mathematical, using the data, some using the biology to try and figure out what these are, and then the mathematics to do that. And so
Couldn't you also do no math and just like guess at values of k that are close to like similar environments?
you could do guess and check. This is a high-dimensional, well, not really a high-dimensional system, but it's not a one-dimensional system. And so guess and check can be a lengthy process.
Yeah.